black hole. So yeah, let's dive right in. So let me just start with this question for you. What do you think is the most mysterious object in the universe? You know, you might picture some crazy colored nebula or a far-flung star, but the answer is a little more complicated than that. Because you see, a black hole isn't really an object in the way we usually think of one. It's a place. It's a region in space where the very fabric of reality, what we call space-time, has been twisted and warped so completely, so violently, that all the normal rules of physics they just fall apart. To even begin to wrap our heads around what that means, we first have to figure out how you even make one of these things. And it all begins with the absolutely spectacular death of a truly enormous star. Think about the life of a giant star as this constant, epic tug of war. On one side, you have the unbelievable, crushing force of its own gravity, always trying to squeeze it into a tiny ball. And on the other side, pushing out, is the explosive power of nuclear fusion happening in its core, which creates just a ridiculous amount of energy. For millions of years, these two forces are in this perfect, delicate balance. But that can't last forever. Eventually, the star's core starts making iron. And for fusion, iron is basically a dead end. You can't get any energy out of it. So that outward push from fusion just stops. All of a sudden, there's nothing holding gravity back, and it wins. Instantly, the star's core collapses in on itself with unbelievable violence, and the outer layers get blasted out in one of the biggest explosions in the universe, a supernova. And if that core that's left behind is heavy enough, gravity just keeps crushing and crushing until it becomes an infinitely small point, and a black hole is born. And that brings us to what is probably the most famous, or maybe infamous, feature of a black hole: this invisible boundary. A line that, once you cross it, you can never, ever uncross. It is literally the point of no return. So this boundary has a name. It's called the event horizon. Now, it's not a physical surface. You wouldn't bump into it. It's more like an invisible waterfall edge in space-time, where the gravitational pull becomes so strong that the speed you'd need to escape is faster than the speed of light. And since nothing in the universe can go faster than light, well, anything that crosses that line is trapped for good. And this is where things get really, really weird because of how a black hole messes with time itself. Let's say you are floating in space, watching your friend fall into one. From your point of view, you'd see them get slower and slower as they got closer to the event horizon. They'd seem to almost freeze right at the edge, getting redder and dimmer until they just faded from view. But for them, it'd be totally different. They would just sail right across the event horizon, probably without even noticing. But in that one single moment of crossing, because time outside is speeding up infinitely from their perspective, they could witness the entire future of the universe flash before their eyes. So nothing can escape. Seems pretty final, right? Game over. But as it turns out, maybe not. It looks like even black holes might not be forever. And it's all thanks to some of the absolute strangest physics in the cosmos. And we call this idea Hawking radiation. The legendary Stephen Hawking figured out that because of all the weirdness in quantum mechanics, so-called empty space isn't really empty at all. It's fizzing with these pairs of virtual particles that pop into existence and then disappear almost instantly. But if a pair of these particles happens to pop up right at the edge of the event horizon, one could get pulled in while the other one escapes. From the outside, it would look like the black hole is slowly leaking, glowing with a faint energy. Which leads to the big question: can a black hole actually die? And the answer is yeah, but it takes a ridiculously unimaginably long time. We're talking trillions upon trillions of years. Over these vast eons, this slow leak of Hawking radiation makes the black hole lose mass and slowly shrink. And then, at the very, very end of its life, poof, it would vanish in one final gigantic flash of energy. Now, all this talk of things falling in and getting trapped might make black holes sound like these lazy cosmic vacuum cleaners just sitting there. But, oh man, that could not be further from the truth. They aren't just destroyers. They're actually some of the most powerful and creative engines in the entire universe. See, things almost never fall straight into a black hole because of a principle called conservation of angular momentum. It's the exact same reason an ice skater or a ballerina spins way faster when they pull their arms in. As matter gets closer to a black hole, it starts to whip around it faster and faster and faster. And what you get is this massive, swirling traffic jam of superheated gas and dust that we call an accretion disk. The friction inside this disk is so unbelievably intense that it heats up the material to millions of degrees, and it starts to glow brilliantly. In fact, this is how we actually see black holes. We can't see the hole itself, but we can see the blindingly bright light from the matter that's spiraling to its doom. And just how bright are we talking? Well, the brightest of these accretion disks, which we call quasars, can be over 1,000 times brighter than our entire Milky Way galaxy put together. They are truly the lighthouses of the cosmos. Okay, so let's do a quick myth-busting round. First, will our sun become a black hole? Nope, not a chance. It's way, way too small. Second, do they suck things in like a vacuum? No. Their gravity is strong, but you have to get pretty darn close to actually get pulled in. And third, are they just cosmic vacuum cleaners? Absolutely not. We're now learning they play a crucial, fundamental role in how entire galaxies are built. So far, we've talked about what black holes are and what they do. But for this last part, I want to explore what they might imply about the very fabric of reality itself. And trust me, this is where things get really, really strange. Einstein's theory of general relativity can be summed up perfectly by this famous quote from the physicist John Wheeler. The idea is pretty straightforward. Something with mass, like a planet or a star, creates a dent in space-time. And that dent, that curve, is what we experience as gravity. It seems like a simple cause and effect relationship, right? But let's go back to Hawking radiation for a second. Here's the absolute weirdest part about it. The radiation, the energy that's leaking out, the math says it doesn't actually come from the black hole. It's generated out in the curved space around the black hole, sometimes a long way from the event horizon. Essentially, the energy is being stolen from the gravitational field, from the curve in space itself, and as a result of that, the black hole shrinks. And this just flips our entire intuition on its head. We think, okay, the foot makes the footprint in the sand. Simple. The black hole's mass makes the curve in space. But what's happening here is more like the foot is shrinking, and that is somehow causing the foot itself to shrink. The change in the curve of space is causing a change in the mass of the black hole. It suggests this whole cause and effect thing might actually go both ways. And that leaves us with this final, truly profound thought. We've always just assumed that matter, you, me, the stars, we are the cause of the curvature of reality. But what if it's the other way around? What if mass itself isn't the fundamental thing? What if we are all just a projection, a kind of shadow cast by the geometry of the universe itself? Black holes don't just force us to question space and time. They force us to question the very nature of what it means